our atmosphere. And that is why we must study atmospheric thermodynamics. So we need to know what is going on in our atmosphere as it affects our day-to-day activities. Now, from there we discuss an ideal gas law, which is also known as equation of state. And then from there it took us to hydrostatic balance and heat and temperature. That's where we stop. Heat and temperature in the atmosphere. So the next topic that we propose to continue is the laws of thermodynamics, then before conduction, convection, and then radiation. From there, we move to water vapor in air, latent heating, and diabatic and adiabatic processes. And the last topic will be Laplace rate and stability in the atmosphere. So these are all we discussed in the last class. I hope you have not forgotten, particularly this equation. These are examples that we work. Now, the first law of thermodynamics. We have been hearing laws of thermodynamics. Laws of thermodynamics. What is the first law of thermodynamics? U is the internal energy. We mentioned an example of using water inside a glass cup as an example to demonstrate internal energy in the last class. You should still remember. So, and the heat energy, which is Q, the work done is W. The first law of thermodynamics therefore states that the change in the internal energy, small change, that is why we use the U, equals to the infinitesimally small change, the heat energy, Q, minus the work done by the system. So therefore, the U, the Q, and the W are extremely small changes in one, the internal energy of the gas, the heat added to the gas, and then the work done by the gas. In expanding its surroundings. In this case, the surrounding is the atmosphere. Please note that the motive for using different notation for both left and right, we are talking of the equation, the previous equation. This the U equals delta Q minus delta W first law of thermodynamics, that is, the internal energy of the system U is a function of state. Don't forget, the function of state. Why the heat produced, which is Q, and W, which is the work done, are not functions of state. Only the U that is related to the state. Therefore, the U is a precise, the actual differential quantity that depends only on the initial and the final points. So, you must bear this in mind, that the U, which is the change in the internal energy, depends only on the initial and the final points. They do not depend on the path taken by the system. So, the path taken by the system doesn't affect the internal energy. But the change in the heat and the work done, they are not functions of state because they depend on the path taken by the system. So the work done by the gas, the heat energy of the gas to heat the gas, depend on the path taken. Therefore, we recall in our last discussion, as mentioned, that the infinitesimally change of the work done by a thermodynamic system are related to the infinitesimally changes of the volume by the following expression. So, we are talking of the volume of the gas. So, the change in work done, therefore, is equals to P dV, the change in volume. The volume is a state variable, hence it takes the form of a perfect differential. But P here is the external pressure exerted on the gas, which is equal to the internal pressure at equilibrium. Any query on this? Do we understand? Am I moving too fast? So we said at equilibrium, the pressure of the internal is equal to the external pressure. Is that what is changing? The volume. It's either the volume increases or decreases. And that is why we have dV. dV means change. And that is why work is done on the system. Anybody having trouble with this before we move on? By putting P dV equals change in the work done in our equation, which is our first law of thermodynamics, this is what we have. Hence, the U now becomes delta Q minus P dV. And what is the implication of this equation? This equation shows that the mechanical work done by the system, they are equivalent. The heat and the mechanical work done by the system are equivalent. Therefore, in principle, we can determine what the mechanical equivalent of the heat in the thermodynamic system. Experimentally, it was found that 1 calorie of the heat equals to 4.1855 joules. The unit of heat is in joules. For example, if we have a situation where there is no work done by the thermodynamic system, I mean, no change in volume. If there is no change in volume, then there is no work done. And then if the work done is equal to 0, so what we have that the gas does not expand, because it's the volume expansion that expands the gas. So if there is no work done, the work done equals to 0. Therefore, the V will be equal to what? 0. And if there are no phase changes or any chemical reactions by the system, we can resolve or evolve the heat. Then, experimentally, it was established that the U at constant volume, which is subscript V, that subscript V means constant volume, will be equal to the change, small change in the heat energy at constant volume will be equal to the specific capacity at constant volume. And what will change? The temperature, the T. The temperature. The T is the change in the temperature. See how we are bringing in volume. By the time we look at volume, now we are bringing in what? Temperature. Connecting all the parameters. I hope you remember that what is driving our climate, what is driving our environmental changes. Don't forget the factors. And the principal is temperature, mentioned in the first class. So, starting with the U equals the Q minus the W, we brought in volume, relating the volume to the work done, which is dV, PdV, the pressure and change in volume. But when there is no change in volume, what will happen? That term, PdV, become what? 0. So, that's why we have dV equals to 0. If dV is equals to 0, then what do we do? That means the internal energy will now be equal to what? The heat supply to the gas. Don't forget, at constant volume equals to the specific capacity at constant volume times the change in temperature, T. So, I have mentioned the subscript V indicate that the specific volumes of gas is held constant at constant volume. Therefore, this process is referred to as isosteric. It's the cable, sorry. The cable is okay. It's now okay. Just as I told you, rehearse your mind. When you see the U, wherever you see the U, small change, the T, you should know that there are a lot of mathematical, in form of calculus, differential equations involved. But in our course, we are not going into all those mathematical jargons, as I said. So, all we need is relate this to environment, our environment. In the last slide, we mentioned CV. Now, this can, no, sorry. This take us to the next expression, a mathematical expression that relates the internal energy to the temperature. And this is what we have. It is called specific heat capacities. We have specific heat capacity at constant volume. We have mentioned that. We also have specific heat capacity at constant pressure. And from our equation of state, don't forget that we have P dV related to the volume, and volume equals density all over mass of the gas. So we have to relate all together. Therefore, the specific capacity at constant volume will now be equal to the change in the small change in the internal energy of the gas, and then small change in the temperature of the system. And putting subscript V shows that it is at constant volume. The volume doesn't change. So by the time we integrate the expression, applying integral, so we now have specific internal energy, which is U, at constant volume. Therefore, U equals, our integral is over a constant volume. And when we have constant volume, that means V1 equals what? V2 equals V3 equals whatever. So, but we still have to put it so that if you don't put it, then it means a different thing entirely. So at constant volume, the specific heat capacity and the change, the product of the specific capacity and the change in temperature is equal to the internal energy. So the subscript on the integral implies a constant volume and integration over isosteric process when we have constant volume. Then what happens when we have constant pressure? In the atmosphere, which is our primary concern, many of the processes are isobaric, meaning constant pressure. They occur at constant pressure so that the change in pressure is equal to, there is no change in pressure, equals 0. So if there is no change in pressure, experimentally confirmed that the heat is added to a gas system isobarically. The heat is related to the change in temperature, which is the T, by an equation similar to the first law of thermodynamics. Therefore, the small change in the heat applied to the gas, which is PQ, at constant pressure equals the specific capacity at constant pressure and then the change in temperature. You can see that we have been saying temperature is the driver. Everything change in temperature. Everything change in temperature. Even when volume is not changing, temperature changes. When pressure is also concerned, we also have temperature change. So that is why it is our principal driver. Where Cp is the specific capacity at constant pressure. Note, for solids and liquids, the specific capacity at constant pressure and the specific capacity at constant volume are essentially similar, but they are not the same for different gases. So, different gases at different Cp and Cv. So, if you have oxygen, the specific capacity at constant pressure and the specific capacity at constant volume is not the same as that of nitrogen or other rare gases in the atmosphere. To demonstrate what we have in the atmosphere in case we put a gas inside the cylinder and then a piston is applied. So by the time the cylinder is pressed down, what happens? Reducing the volume, and then by the time the cylinder, the piston is released, we are increasing the volume. So when we apply heat inside a gas cylinder through a piston, which is this, there will be some combinations of an expansion of the gas. That is, work is done by pulling up the piston, and then this will cause an increase in the temperature, which is the driver and the principal driver. The increase in the internal energy at the same time of the gas. So the mathematical expression is so this shows that when we move from P1, P2, this is the pressure, and then the volume, V1, V2. So when we move from V2 to V1, we reduce what? The volume, the change in volume. And then when we move from V1 to V2, we increase the volume. This is what happens when we have this system. The change in the internal energy, U, will now become rho theta alpha plus CV theta T. The heat applied to the gas is equal to the work done by the gas plus the change in temperature. Theta alpha here is the change in volume of the gas, and then the CV, which we have been mentioning, is the specific capacity at constant volume. So the specific enthalpy of a gas now combine all these equations we have mentioned previously. We combine them together to form the first law of thermodynamics as follows. The change in the internal energy equals to a very small change in the heat, the quantity of heat applied to the gas, minus PdV equals the small change minus the small change in PV plus VdP. Combining all together. Is there anything here that you don't understand? You understand all the terms, because you have to take it step by step for you to understand. But if you don't understand, you can always call me back. Then I explain. Is it clear? We can move on. We can further simplify this equation. Putting the terms together, plus PV now equals theta Q plus V dP. U plus PV on the right hand side should be on the left hand side, sorry. Should be on our left now as we are looking. This is our left hand side. It should be on the, so sorry for the typo. It should be on the left hand side. It's called the specific enthalpy. This term U plus PV is called the specific enthalpy of the gas, denoted by H, small letter H. Don't get it confused with our height. We use capital H for the hydrostatic balance height in our last class. But now this one is small letter H, and H equals U plus PV. Putting H in the equation of the first law of thermodynamics, this is what we have. Instead of having the U in our thermodynamics equation, we now have the H. Change in specific enthalpy. What is enthalpy? When we say enthalpy, huh? You have not had entropy, enthalpy in your chemistry? Maybe you already forgotten. Long time. We are talking of when a system either releases it or absorbs it. Huh? So this is the H is equals to the quantity of heat, small change in the heat, and then the small change, the volume at that change in pressure. Is there anything confusing there? Sir, you like, is there anything confusing? So we can explain further. It's just replacing one atom with the other as they are connected together. And you can see that from this equation, our temperature is not there, but the pressure and the volume. We can put this one in our equation for constant pressure isobaric process. So we now have the specific capacity at constant pressure Cp equals the change in the enthalpy, and then bringing in our temperature now. The rate of change of enthalpy with respect to temperature at constant pressure. So therefore, our enthalpy now is equals to integral specific capacity at constant pressure times change in temperature. If we don't know the change in temperature, and we have to calculate the specific enthalpy of a system, a gas system, this is the equation we have to apply. We know the change in heat, the volume, and then the differential pressure, the change in pressure. But if we are given the change in temperature, the specific capacity at constant pressure, then we can now apply this equation. determine our specific enthalpy of the gas. So the result script as before denotes constant pressure, which is an isobaric process. These are just examples of some constants that we'll be using in the nearest future. Specific capacity of a substance is the quantity of heat. When you are defining C, small letter c, don't forget quantity. The amount of heat energy required to raise the temperature of any substance. The unit must be the unit of that substance at a given temperature of 1 degree, a change of 1 degree. So when you have a substance and then the temperature of that substance changes by 1 degree Celsius, then the unit of that substance in kilogram, which is 1 kg of the substance, the quantity of heat required to change that substance is referred to as specific heat capacity of that either gas or materials or anything. But in our own case, we are dealing with atmospheric thermodynamics. So mostly we are referring to gas, gaseous state, gaseous material. So here, the calorie is in gram per Kelvin, or the specific capacity is in joule per kilogram per Kelvin. And then for ice, sound, and most importantly, water. This is common for the 200. Maybe from our college level, we have been hearing this specific capacity for water for the 200 joule per kilogram per Kelvin. So those are an example for us in case we need to use in the future for our computations.